So initially what I did was first render the Roomba and leash as well as the pillars. Next, I needed to be able to determine the target point that my mouse corresponds to. So based on the mouse's position, where should I move the Roomba to? I took the OF point, which corresponds to the mouse position, and for every triangle in the mesh, checked to see if that point was contained in the triangle. The triangle that contains OF is then shaded orange, and the target point is set to the circumcenter of that triangle. We note that we also had to write an algorithm to identify if OF was not contained in any triangle, in which case we would find the closest edge to OF and choose a triangle that contains that edge, which you can see here. We then generate the potential points that, from the Roomba's current point, the triangle can go to. This was simple. We simply calculate the circumcenter of the triangle of the opposite corner, my next corner's opposite corner, and my previous corner's opposite corner. These were the three options, in addition to staying at the point itself, and these options are rendered in pink. We then choose the best option by calculating the distance between each option, including just staying there, and the target point, and choosing the one with the minimum distance. The choice that is the best is shown in gray. I then put everything in a while loop and ran this code while the distance between the target and Roomba was not less than the step size, regenerating new choice options only when the Roomba is at a circumcenter. For this check, we generate the circumcenter of the triangle that the Roomba is currently in, and then check to see if the distance between the target point and Roomba is less than the step size. This algorithm must loop through all triangles, which is admittedly inefficient. Only if this distance is less than the step size will we generate new options for the Roomba to travel to. For step 8, we create a greedy algorithm. We simply generate a list of all the circumcenters and throw them into a minimum heap sorted by the distance between the circumcenter and the current point. So we first set the Roomba's position to this current point. This allows us to choose a starting point that is the circumcenter that is closest to the Roomba. We then clear this heap and put all the remaining vertices back into the heap, now sorted by a different current point. This time the current point is set to the previous popped out point. When we now pop out a new point, this point will be closest to our previous point. We continue until all the circumcenters are chosen. This is a greedy and inefficient algorithm, but it does the job fairly well. Once we have a list of all the circumcenters in the correct order that the Roomba should visit, such that with each step the Roomba visits the closest next point, we set the target position that the Roomba should go to the head of this list and tell the Roomba to travel to the target in step size equal to 3. We remove the head of the list when the Roomba reaches this target, set the head of the list to the next point in the path, and then continue until the list is empty. However, since we used a simple lerp to get from one point to another in the path, this would sometimes cause the Roomba to go off the Voronoi edges if the next point was not a neighbor to the previous point. To circumvent this, we create a check, is neighbor. If the previous point in the list is not a neighbor to the current point, we then perform a greedy pathfinding algorithm that simply performs step 7 automatically. Essentially, this greedy subroutine will generate 3 choices, similar to step 7, that the Roomba can take, and will choose the choice that has the closest distance to the target. We then recurse until we reach the target node. Finally, we add all of these nodes to our master path list for step 8. We note, the isNeighbor check contains a check to find the triangle of a circumcenter that loops through all triangles, so this algorithm is pretty inefficient. Moreover, this subroutine itself has the same running time as the pathfinding algorithm, so this greedy algorithm is pretty inefficient. However, it does get the job done and minimizes the travel distance pretty reasonably. We have painted dots on all of the circumcenters, and we will remove the dots once the Roomba clears the triangle and visits that circumcenter, to more visibly show the Roomba's path. We also add this lime green color. For the user control portion, we first reset the Roomba's position. This user control portion of part 2 of step 8 can be triggered when you press 8 twice. Note that this mode only works after the automatic Roomba algorithm runs. Essentially, this mode reinstates step 7 code, since it works perfectly fine for this scenario. The only change is that it keeps track of which circumcenters you have visited. Once you visit a circumcenter, the code will stop rendering a ball in the circumcenter, and it will jot down that you visited this circumcenter. Once all circumcenters have been reached, the algorithm stops, and compares your score with the computer score. We show step 9. Essentially, I followed the math that was provided in lecture, and for each ray shooting out, I checked if it hit any of the vertices, and if so, I chose the vertice that was closest to my Roomba position. Unfortunately, as you can see, this code doesn't really work, and I did not have the time to implement the rest of this code.